going to talk about the concept of power and efficiency and solve related problems. So power is defined as force times the velocity. Power. So power is denoted by P, and that is the force, which is a vector, dot with the velocity. Okay, so force and velocities are vectors, while if you take the dot product, then you end up with a scalar. So that's a single number. Okay, and it really comes from, the power comes from the force, the work done. So work done is F dot ds. So this is something which we did last time, right? So if you take the time derivative of the work done, you get power. So power is the time derivative of that, and that is V. Okay, so I took a shortcut, I did not quite derive it, but you're going to take the derivative of f with respect to time, which is 0, and then take the derivative of s with respect to time, which is v, and that's how you get f dot v. The way power is expressed is in this. So you can, in SI units, power is given by watts or W, and there's another way to do it. This is in horsepowers. Okay, that is 746 watts. Is 1 horsepower, and you can also convert between horsepower and FPS, foot-pound system. So 1 HP is 550 feet times weight divided by time. Okay, so this is SI and this is FPS. So really the history behind power, work done power, is that there were no cars and there were horses, and a horse is used to, the output power per horse was around 746 watts, and that's how horsepower is more common than using watts. So when you buy a car, it is rated in horsepowers and not by watts. That's the reason. So other thing is efficiency. Okay, and efficiency is will denote it by, I guess it's called epsilon in Roman. So epsilon is the output power, power out, power input. Okay, so P out to P in. Okay, and the reason why the output power will be different from the input, well, efficiency, by the way, is always less than or equal to 1, because if it was greater than 1, then it means that it's not a realistic world in that case, because you cannot have the output power more than the input power for a particular system. Now, the reason why the output power is different from the input power is because there are inefficiencies in the system, like there could be friction, there could be drag, and so on. Okay, so that's it. So let's try to use this and what we learned last time and solve some problems. Okay, another thing about power is that, do you know what the, so efficiency is that, do you know what the maximum efficiency of the muscle is, human muscles? So a motor you can go up to 80 or 90%, depending on so okay, efficiency is not constant. Okay, for a motor, it varies as a function of speed. So it's about 80% if you go very fast. If you go slow, then the efficiency decreases, and when you're at zero speeds, the efficiency is zero. Do you know what the efficiency of muscles is? Maximum possible efficiency of muscles? Can you make a guess? No guesses? 0%? It's about 25%. You cannot have muscles more efficient than 25%. The maximum efficiency of muscles is 25%, which is terrible. It comes off motors. But humans are somehow, well, you can see that humans do better than, well, in case robots, which are typically slow and jagged. So it's not just a power source, but it's also how we control things. Yeah, so I'll talk more about this and probably show you some videos later on the same idea about muscles and so on. So here is a question which involves power efficiency. So let's read it. So 10-pound collar starts from rest. So this is the collar, and is lifted with the constant speed of 2 feet per second. So this goes up at the speed of 2 feet per second along the smooth rod. So that means there's no friction. Determine the power developed by the force at the instant shown. So at this instant of time, you got to find the power developed by this force. Okay, is that clear? So when you pull the string F with the force F, the collar moves up with a constant speed of 2 feet per second, and clearly there's a force which moves it up, and there's a speed, so you can compute the power. So let's try to first draw the free body diagram. So essentially the recipe is the same. You draw a free body diagram, then you can use the power equation. Sometimes you have to write the equations of motion because you're interested in forces in order to compute the power. So it really depends on what you're asked. So free body diagram. And I'm going to draw a free body diagram of only the collar because the collar is going to move upwards. So since the string is inextensible, the pulley doesn't have mass, the force in the string is F. There is going to be well, this is not given here, but there is, of course, gravity. Right? Yeah, there is gravity. So since there's gravity, that's going to be mg downwards. And since I've removed the collar from the rod, okay, I have to replace the effect of the rod with a force, and that force is going to be in the normal direction, right? Because if there was no such force, then this collar would not have stayed firmly in that position. It would have moved in the horizontal direction. So there has to be a force. Is there a force in the y direction or the upward, downward direction here? No, because there's no friction. If there was friction, yes, you would have had to put it there.
Professor?
Yeah.
How do you determine the normal in this case?
Really, you can put it either way. In this case, actually, the normal direction I assumed is wrong. It's going to be this way. When you do the math,
Our sign will come out.
the sign will come out. So if you do the equilibrium in the x horizontal direction, you see that n should have pointed that way and should be equal to f times sine of theta. So as I said, don't worry about the sign. So all problems in this course, you can assume whatever you want for the reaction forces in terms of direction. However, for friction problems, you cannot do that. If you do that, if you assume the wrong direction, it may happen that you'll get the wrong answer. Okay, so don't do that for friction problems. So equations of motion. In this case, all I care about is the force F. So I do equilibrium in the y direction. So let's call the upward direction as the positive direction. So Fy is mass times acceleration in the y direction. The force in the upward direction is the net force is F cosine theta with a positive sign because it's upwards. There's mass times gravity acting downwards. right, with a minus sign. What is the acceleration? It is 0. Why? Because you're told that the collar goes up and down with constant speed. Okay, so F is moving mg on the other side. I get mg divided by cosine of theta. Okay, the final thing is to find the power. Power is F dot V. Okay, now F acts this way. It acts at an angle, right? And the velocity is upwards, or yeah, upwards. So what I can do is, well, there are two ways I can do it. I can write F as a vector, okay, and then take the dot product, or I could just put F with the right sign. Or I could just find the components in the x direction in F dot V and the components in the y direction and then sum them up. So that might be easier. So I find F x V x, right, plus F y V y. And the reason is because F is Fxi plus Fyj, where Fx and Fy are the x and y components of the forces, and the velocity is going to have a Vxi plus Vyj, right, as an x and y component. This is a general case. Now I'll of course put values to that. So Fx, Vx, Fy, Vy. What's Fx? What's the force in the x direction? So x is this. So it's F sine theta times velocity in the x direction. That's 0, right? Because the collar can only move up and down. What's the force in the y direction? It's F cosine theta. And what's the velocity in the y direction? That's given to us as 2. Or I'll just put it as V. I'll call this as V. Okay, so V is given, F is not given, but I did find what F was. So from 1 and 2, power is mg cosine theta times cosine theta, right, I sub this in, times V. Okay. Now I also have to be, so when I wrote this down, I also have to be careful about the sign. Turns out that F cos theta is upwards and velocity is also upwards, right? So the sign is okay, this is positive. Otherwise, I would have had to put a negative sign if it was moving the other direction. So those two cancel off. I'm left with P is mgv, and if you put the values in, what you get is mass, gravity, and velocity all are given. So it comes out to be 644 pound feet square divided by second square. So the way you can find the units is, you know the units of mass, that's lb. Gravity is feet per second square, and then velocity is feet, I think it should be c, s cube. I just put the units, lb. Units of gravity is feet per second square, and velocity is feet per second. So if you multiply all of them together, you get that. So that's perfectly fine. Now sometimes you don't have to. Yeah, question.
That's pound mass or pound?
What's that?
Is the 10 pounds pound mass or
Pound weight. I interpreted that as just the weight. I mean the mass and not the weight. If it was weight, then mg is 10. So I interpreted. So let me write this down because that might confuse people. I interpreted m as 10 lbs, but if it was pound force, then mg would be 10 lb. Yes. So the way they've given it is I interpret as. So your answer would depend on how you interpret that. It doesn't say there'll be weight. I thought it was just kgs. You give weight? So if it's weight, then this would be divided. You need to divide it by 32.2, and that's the answer. So I used 10 times 32.2 times 2. Okay, I can assure you that I'll be very clear in my question for the exam. I will not make it so vague. Okay, let's solve. Yeah. Yeah.
Can we, just curious, could we just find theta since we're given the dimensions and do absolute value of f, absolute value of v times cosine theta? to find power?
But you're not. Yeah, you can find theta.
Can we just do that? F times v cosine theta since we're doing it's a 3 4 5 triangle.
No, but cosine theta doesn't come up in the equations. It cancels off. No, that's not true. We'll do a problem a little later. When? Sorry. Yeah, next problem where it depends on theta.
So why won't that work in this case?
Oh, it's absolutely fine if you find the value of cos theta and go to the math. Just that cos theta cancels off from the equations. The final answer power does not depend on theta. Just this is how the problem is set up. It's not in general true for all problems.
Okay.
Like if I told you what is the work done by mg, well in that case also sorry, there will not be any theta coming in. Because mg times v will be the work done. So so it just happens that the problem is not dependent on theta. Yeah, question.
Is this the weight already mass times gravity?
Yeah, that's right. So what I'm trying to say is that the question said 10 lbs. I interpreted it as 10 lb, and I thought that a better way to define weight would be, well, if they wanted to say weight, then they would have said 10 lb force or something like that. That means that 10 is lb in the units of mass times gravity. So if it was that way, I would have taken it to be 10 times 2. So the answer would be 20. But I interpreted that as 10 lb, and there was no gravity in that. So there's a bit ambiguity. Okay, I can assure you that I will not give you a problem in foot-pound system. I would give you a problem in MKS because that is the units used for perhaps all computations. Okay. Okay, so next question. An automobile having a mass of 2 mg or 2 megagrams travels up a 7-degree slope at a constant speed of 100 kilometers per hour. If the mechanical friction and wind resistance are neglected, determine the power developed by the engine if the automobile has an efficiency of 0.65. Okay, so the question is, this automobile is going uphill. Okay, it has a certain weight. It's going at a constant speed. It's not accelerating. You've got to find the power developed by the engine if you're given that the efficiency of the engine is 0.65. So you want the power which the engine is using to go uphill. However, since the efficiency is 0.65, the actual power would be more than what is needed to move it uphill, right? Because it's only 0.65 efficient. So what I'll do is first I'll find the power needed to move uphill, and then using the 0.65 I can find the actual power needed by the engine. So again, draw the free body diagram for the car. This is a particle problem, so it doesn't matter if you draw it as a point mass. Okay, so there's a normal force. Okay, and remember that the car is being driven by an engine, so there is a force which is driving it uphill. So I'll call that F. So this is the engine force. Okay, from engine. Okay, if that force did not exist, what will happen? The car will just slide down, right? Okay, so Let's do the equations of motion. Okay, so I'll say that this direction is x, the upward direction is y. In this case, in order to find the power, I need the force, or the force from the engine, which I'll then multiply with the velocity, which is 100 kilometers per hour. So F is positive. And then there is, what other force acts in the x direction? Mg sine theta, right? Because this angle here is going to be theta, and so I'm interested in the component along the x direction. So it's mg sine theta equals mass times acceleration. So what's the acceleration? It's 0, because this is moving with a constant speed there, right there. So that is equal to 0, which means that the force developed by the engine is mg sine theta. Okay. So F is the force created by the engine. So then I can use the power equation. Power is simply F dot V. Okay. Again, there is a force in the x in the y direction. Well, in this case, there's no force in the y direction. The car is not developing a force in the y direction. So the only force is mg sine theta. Okay, and that is to the right, right? F is to the right. It's positive. The velocity is also positive and to the right. So the product of force times velocity is positive. So the mass is 2 into 10 raised to 3 kilograms, right? Because 1 megagram is 10 raised to 3 kilograms, and the weight was given to be 2 megagrams, times 9.81 for gravity, sine of 7 degrees, because that's the slope, times the velocity is 100 kilometers per hour. I need to convert that into meters per second. So 100 kilometers is 1000 meters, and hours is 3600 seconds. So this is meters, this is seconds. That's how I convert kilometers to seconds. This is wrong. This is 100. This is in kilometers. So I convert that into meters per second. So if you do this multiplication, then you end up with 66.4142 kilowatt. Okay, so this is the power which the car, well, this is the power which is needed so that the car moves at a speed of 100 kilometers per hour upwards. Now, the efficiency is defined as the power out divided by the power in. Okay, so the power out is 66.42, right? That is the output power from the engine. The input power is unknown, and the efficiency is 0.65. So from that, P in is about 102. Is 102 kilowatt. So that's the answer. Okay, any questions on this? No question. This is fairly simple. It's really as simple as draw the free body diagram, find the force you need, and only write that equation which will give you that force. Once you get the force, you can find the power by multiplying it with the velocity. The mapping to 10 feet per second in 4 seconds. Okay. If the acceleration is constant, find the power that must be supplied to the motor when time t is 2 seconds. The motor has an efficiency of 0.65. Okay. So the acceleration is constant. Okay, so what would be the velocity time graph? It'd be linear. It'll start from rest, go up 4 seconds. At 4 seconds, the speed is going to be 10 feet per second. Okay, so there is a motor, and it's spinning at such a speed that it is applying a torque such that the 50-pound crate is moving at constant acceleration. Okay, and that's why you get that velocity time profile. What you're asked to find the power supplied by the motor. Okay, so if you want to find the power supplied by the motor, all you have to do is find the force that the motor is supplying, and the force times the velocity will give you the power. Right? So let's just start with the free body diagram. FBD. Okay, so in this case there is a motor, there is a pulley, and there's a crate. So what I'm going to do is start with the mass because the crate is moving upwards. And I think if I start from there, I have a better idea in solving this. So there's a tension T, which is opposed by mg, and I need to choose a coordinate axis. I'm going to choose y as going upwards. So then there is this pulley, so this tension should be the same as that tension because this is a free body diagram of that pulley, and so this is going to be T divided by 2, T divided by 2. Okay. Okay, well, actually, I could. Well, it's okay. So I was thinking maybe it's better to define T as T here and then 2T, make it 2T, but this is fine. It doesn't matter. Okay, so that's the free body diagram. Next is the equations of motion. And what I'm really after is two things, force and velocity. Okay, I think I'm given the velocity. Oh no, I'm not given the velocity. I'm just told that I need to find the velocity at time t equals 2 seconds. So this is what I'm really after. I need to find the power at t is 2 seconds, which means that I need to find the force at t equals 2 seconds and then multiply it with velocity at t equals 2 seconds. Okay. The velocity is not constant. It is, as I've shown here, it changes with time. So I need to find the velocity at 2 seconds and the force at 2 seconds. Now, the way I can get the force is if I can find the tension in the cable, I'll get the force. Okay, and the velocity can be obtained from this graph. So first thing I need to do is find the tension in the string of the cable. So that's why I have these equations of motion. So Fy is mass times acceleration in the y direction. This is for the mass. Mg is with the negative sign because mg is in the opposite direction of y. The tension is upwards in the positive direction, and mass times A is upwards. Okay. In this case, acceleration is not 0. It is constant, but it is not equal to 0. Okay, so I am interested in finding the tension. So tension is mass time. I'm just moving this around to get G plus A. Okay, so if I can find A, I can find the tension. I know what the gravity is. I know what the mass is. And the way I can find the acceleration A is by doing kinematics using this plot. Right? I know that the speed, the acceleration is constant. I also know it hits a velocity of 10 feet per second in 4 seconds. So I'm going to use kinematics to find basically this plot to find acceleration. Okay, so velocity is, since I am interested in the relation, I know velocity and time, I'll look at that equation in the kinematics. There are three equations. Velocity square, uh, velocity square is velocity 0 square plus 2ax, that's velocity and s. There's a velocity and time relation, and then there's a relation between s and t. So out of those three, the only expression which makes sense is this one, because it has v and t and also a. So the velocity is 10, initial velocity is 0, initial velocity is 0, acceleration is constant, and the time is 4 seconds. So from that, I can find the acceleration is 10 minus 10 divided by 4 is 2.5 meters per second square. Okay, so now I can find the tension equals mass times, so mass is 50 lb. Okay, I'm going to interpret that 50 lb as lb, not lbf. Yeah.
Would that be 2m? The mass of gravity over.
You mean this here? No, it won't be 2m because this is the tension. If this was something else, t divided by 2, it will be t. Okay, so the tension is mass. So I'm going to interpret 50 lb as 50 lb and not 50 lbf. If it was 50 lbf, then mg is to be taken as 50 lbf. Okay, so I'm going to take it like that, and it's absolutely, so in the exam, if you're confused, just say I interpreted this as 50 lbf or 50 lb, and that's fine. It's not a problem because the question is not very clear if it's lb or lbf. So 32.2 plus 2.5. This is wrong, by the way. The units are feet per second square. So this comes out to be 867. Okay, it's 434. I get 434. Okay. What I need to do now is find the velocity at time t equals 2 seconds. So that is simply v0 plus at. So that's 0 plus acceleration is 2.5. The time is 2. So that's going to be 5 feet per second. I need to find the tension. Now the tension here is the tension it's the tension in the motor. It's not the tension in the, one sec. Okay, my bad. Sorry. It is this tension, sorry, it is this tension. The tension at t equals 2 seconds is the same thing I found here, it's 434 lb feet per second square. Is that right? What's that? Is it not 434? Oh, it's double of that, my bad. Yeah, I did it slightly differently here, so it should be 867 times 2. It should be 1734. 1734, my bad. Yeah, it should be 1734. So then 1734, and so the power at t is 2 seconds is 1734 times 5. Okay, that comes out to be 8675. Is that right? Can you check? 8670. 8670. So that is the power I was after, but now I need to find I want to find the actual power. The actual power is the input power. The input power is the P at t is 2 seconds divided by 0.65, and that comes out to be, see, divided by 0.65. So it's 1338. 1338.46. Yeah, the units are lb feet per second square. Okay, so that's